How's it going, everyone? Welcome to the last video on transition matrices. Today we're going to have a look at just a couple of examples working with transition matrices. So to start off, we've got example 20, and we've got the matrices 1, A, B, and C. Question asks to evaluate each of the following. So we're using CAS, so get your calculator out and follow the steps. Okay, first one, we've got matrix A, and we want to work out what A cubed is. So there's a couple of different ways we can do it. First up, just putting in the matrix. And we want it cubed, so it's just to the power of 3. Then click enter, that's your answer. So that's A cubed. Another way, and we've had a look at this in an earlier chapter, we're going to store this matrix. So using that little arrow button, and we're going to store it as matrix A, so I'll type in A, click enter. So that means every time we type in A, we're going to get that matrix. So just testing that, type in A again, click enter, we'll get that matrix. Now we actually want A cubed, so if you go back up and fix it so it's A to cubed, we should get exactly the same answer as we got before. Okay, so two different ways, get you the same answer. This second way will probably be more useful as we get into transition matrices. So it's good to know how to do that, but you can still work it out by using the other method. It's up to you. Now I'll let you have a go at typing in B squared. I'm going to have a look at matrix C. So again, get your matrix. So this is a 3 by 3 this time. Oops. Okay, so we got matrix C. Again, I'm going to store it as C. Enter. So again, every time we type C in, we'll get that answer. So we'll type C, and we're putting it to the power of 0 this time, just to see what happens. And interesting enough, we get the, if you recall, the identity matrix. And that's because basically if we talk about any number and we put it to the power of 0, we're always going to get 1. So anything to the power of 0 is 1, and our identity is technically our 1 matrix. Now part B says to evaluate C to the 40. So quite a big jump. So we've got our matrix C, and I'm going to put that to the power of 40. And when you put to high powers, it generally takes a little while to work out. So we've got these lots of decimals, really big matrix. I'm actually going to put it to what's called standard, so it's going to put me into fraction form, hopefully. So just a little button down here, so you can change it from decimals to fractions or whatever just by tapping that. So again, click enter. And that's probably even worse. That's huge. So go back. That does not help us. Okay, so again, we've got 0.3 recurring basically for each of the elements. Question asks to express the matrix in whole numbers multiplied by a fractional scalar. So, if I go back to my drawing board, we've got matrix C as 0.333 recurring, and that's for each of those numbers, every element in that matrix. I'm not going to write it out. So it asks to express a matrix in whole numbers multiplied by a fractional scalar. So I can actually say that 1/3 is 0.3 recurring out the front, and then we'll just have the elements 1, 1, 1, 1 all in there. Okay, that's what I was hoping the calculator would do, but it actually made it worse. Didn't work. So just to recognize that we've got 0.3 recurring is the same as 1/3. I could have written each of these as 1/3 in there. So I can take that out as a fractional scalar, and then I've got ones all in there. So that's all it is for part C, or part B. Next example, we've got example 21. So represent each of the following as a transition matrix. So this is similar to last video. So we've got from and to, and looks like we've got A and B, A and B. So it looks like it's train carriages between two depots, however you say that. So we've got from A and B to A and B. So look at A. This is where they start. Where they end at the end of the day, 0.32%. 32% of them end up there, if that's what we're talking about. So they start at A in the morning, end up at A at night. They start at A in the morning, end up at B with 0.68. From B, end up at B is 0.55, and this one is 0.45. So start at B, end up at A is that one there. Okay, so we can actually say that our transition matrix T is just 0.32, 0.45, 0.68, and 0.55. Now, part B says there's a number of train carriages operating between the two, north and south. At the end of each week, 40% of the carriages started at north and ended up at south. 25% had started at south, ended up at north. So we got to identify that there are two states, north and south. So enter the percentage probabilities in decimal form. So we've got so we've got 40% of the carriages started at north, ended up at the south. So from north to south, so I got 40 over here, 0.4. And the next one is 25, started at south, end up at north. Okay, and the remaining two elements, if you remember, each of the columns need to add up to 1. So if we've got 40% here, we need 60% here, which is 0.6. and we've got 0.75 over here. So it's just adding the columns up to 1. So that was part A, that's part B. And that's it. So that's our, or actually I should say my transition matrix. Okay, so that's my transition matrix, I should say. Anyway, next one, example 22. So we've got a survey showing 70%. A survey shows that 75% of the time customers continue to purchase their groceries from A if they purchased their groceries from store A the previous month. Whereas 25% of the time customers will change their purchasing their groceries from store B if they purchased from store A the previous month. Okay, so I've got a bit of information there. So use a matrix recurrence relation to determine how many customers are still purchasing their groceries from A and B at the end of 2 months. If we've got 300 starting at A, 300 starting at B. Well, straight away, we can look at that. So we've got 300 customers starting at A, 300 starting at B. That's going to be our initial matrix. So we've got 300 from A, 300 from B. Next thing to look at is our transition matrix. So if they shopped at store A the first month or B the first month, okay, how many of them shopped at A the next month? So that's going to be 0.75, 75% of the time. Which means we've got 25% shopping at B the next month. So if they shopped from B the first month, what happens? How many change to A the next month? Well, that's going to be 20%. Sorry, B is 80%, which leaves 20% over here. So we've got 80% of the time customers from B purchase their groceries from B the previous month, which leaves 0.2 over here. So basically our transition matrix, we just need to get rid of all that. So that's our transition matrix. And the question is, we need to work out the matrix recurrence relation to determine how many customers still purchasing at the end of 2 months. So at the moment, we've got S0, meaning the starting point. So at the end of the first month, we're going to have S1. And S1 is determined by our transition times the previous month, which is S0. So our transition as we worked out over here, and our S0 is the initial state. Okay, and so we just got that multiplication to do. Probably use our CAS, and we should get these two. Okay, so we've got 285 people shopping at A the next month and 315 shopping at B. We need to work out what happens at the end of 2 months. So we've got 1 month, now we need to do the same thing but for 2. So I'll just add a new page. So we've got S2 That's going to be our transition times the previous month, which was S1. So I've got my transition matrix in here. And I'm multiplying it by the matrix we just worked out previously, which was this one here, 285315. And if we do that, put in our CAS, work it out, we'll get 276.75 and 323.25. Okay, so we've got 276.75 people shopping at A. So I actually say 277 customers will be purchasing their groceries from A, and 323 purchase from B, and that's after after 2 months. Okay, so that's part A. Part B, what percentage of customers are purchasing their groceries at A and B at the end of 6 months if 50% of the customers started at A? Okay, so I'll go, we'll go a new page. Okay, so we've got 50% of the customers starting at A. So we've got a new initial state, and we'll put it as whole numbers as percentages. Okay, so we've got 50% starting at A, which means 50% start at B. We've got our recurrence relation from our previous video, S of n equals t to the n times S0. Basically what we're saying is, from our past, from part A, I could have worked out S of 2 simply as t to the power of 2 times S0. Because we're multiplying by t twice, so we've got 1 in the first one and then 1 in the second one, basically we get squared, and what's left over is S0. So that's our recurrence relation. What we're working out is S of 6, because we want what happens after 6 months. So we've got t to the power of 6 times S0. So it's only one calculation we need to do. We've got our matrix T doesn't change, but we've got our matrix S0, our initial state, changed. Because we've changed them into percentages, we don't know how many customers start specifically in this example. So just finish the transition. And we multiply it by our new initial state, which is 50 and 50. Remembering this is in percentages. Do that on our calculator. What do we work out? We get 44.5982 and 55.4018. So basically 45% customers will be purchasing from A, and that leaves 55% purchased from B. Okay, and remember this is after 6 months. Okay, so that's part B. We'll have a look at worked example 20. So we've got the Better Health Centres running concurrent lift and cycle fitness classes at all 3 of the gyms. So we've got 80% of the clients attend a lift class 1 week, will attend lift class the next, while 20% move to the other cycle class the next week. 70% of the clients who attend a cycle class 1 week will attend the cycle class the next, while the other 30% will move to the other one. Okay, so the numbers also affected by people joining and leaving the gym, an additional 2 people joining the lift class each week and 3 people joining the cycle class. So in the first week, 55 people attended the lift class and 62 attended the cycle class. Okay, after reading that little bit there, it's going to be my initial state because I've got 55 people attending the lift class and I've got 62 people attending the cycle class. It's my initial state in the first week, so that's my initial state. So it's always good to write down as you read it and you pick out, okay, well that's my initial state. I'm going to write that down straight away. So the actual question says, set up the matrix recurrence relation that would be used to find how many people attend the lift class in week 2. So we've either got lift or cycle, lift or cycle. Okay, this is the first week. What happens? How many people go to the same class the next week? So going back up and reading the information, we've got 80% of the clients who attend the lift class 1 week will attend the lift class the next week. So we've got week 1, the next week. Okay, we've got 80%, so 0.8. So that's the first bit. Well, the other 20% move to the cycle class. Again, that information we can actually work out by just going 0.8 plus this one has to equal 1, so 0.2 or 20%. So from the third paragraph, we've got 70% of the clients who attend cycle 1 week will attend the cycle the next week. So we've got 0.7 over here, which means we've got 0.3 remaining here. As it says here as well, so we've got 30% moved to the other class. The other thing is we've got one more condition. We've got the numbers affected by people joining and leaving the gym. So we've got 2 additional people joining the lift class each week. So I'm actually going to make matrix B, and we've got 2 people joining the cycle class. The lift class, sorry. And we've got 3 people joining the cycle class each week. So again, we've got lift and cycle. This is lift and cycle. So before I've done anything else, I need to set up the matrices as shown. So we've got our transition matrix. So we've got an initial state here, that's good. We've got also our transition matrix, which is just this one here. Now, I actually should say this is the first week because we've got in the first week, so S1, S0, either way, it's going to be the same. It just depends how we write it. So that's our initial state matrix. And basically, we need to work out so who attended the lift cycle in week 2. So it's just S2, and that's going to be our transition matrix times our initial state, which was the previous week, and we've also got this matrix B. Because we've added 2 more people, we've added 3 more people. So again, just need to use our CAS, work out, put those numbers in, and well, so we don't even need to work it out. It's just asking us to set up the matrix recurrence relation. So we could go further, but we just put in the numbers. Times our initial state, and we've got plus that matrix there. So we could work out what that is by putting in our CAS. I'm not going to do that at the moment. You can do that if you want. And so we can use that to work out what happens after week 3, week 4, etc. And we can see the change in that. So really this question is just getting you to practice getting those 3 matrices there. That's going to be the hardest task. This is probably just as hard, but this one is probably the hardest, is getting the information into our matrices. Okay, again, we've got another long question. Example 24. So, a school running extra math and English classes each week, students being able to choose which extra classes they want to attend. And they've modeled it with the matrix equation, which determines the number of students expected to attend extra classes is given by. So here's our matrix recurrence relation. So we've got Sn is the column matrix that lists the number of students attending in week n, right? So the attendance matrix for the first week. So there's our initial matrix. And part A says calculate the number of students who are expected to attend extra English lessons in week 3. So we're looking for S of 3. And S of 3 is going to be this matrix here times by S of n, which is going to be the previous month, which was S2, which we actually don't have. We've only got S1. I'm just going to put it in there for now, just as S. Sorry, no, that should be S2. Yeah, and then take this matrix here. Now, I can't work that out because I don't know what S2 is. So I'm actually going to take a step further back and work out what S2 is. So S2 is actually going to be the same matrix as in there, times S1, take that last little matrix there. And I know what S1 is now, because that's given me at the start. So if I rub that out, put that in. And I can work out what S2 is just by using CAS. And if I do that, I'll get 109 and 71. So now I can use that into this one here. So S3 is going to be that, which again, I can just type that in the calculator, and I should get 107 and 57. Okay, so that's all we need to do. So really, we needed to start with S2 so that we can get S3. The other option is, if you remember, S of 3 is going to be our transition to the power of 3 times our initial state. Okay, but the problem is we've got this number in here which will affect it. So it's just as easy to do it through stages. We don't need to do too many. Okay, just work out what S2 is so we can work out S3. So there's 2 steps there. Part B says, of the students who attended extra classes in week 3, how many are not expected to return for extra classes in week 4? So this just means that we need to work out what S4 is. So week 4 is going to be our transition times the previous calculation, which and we take away and we should get 101 and 47. Then we just need to work out, well, we've got a total in week 3 and total in week 4. So in week 3 we had 107 plus 57, so 164. In week 4 we had 101 plus 47, so 148. So the difference is going to be 164 minus 148. So we've got 16 students. So it's estimated that there were 16 students that attended extra classes in week 3 that didn't attend in week 4. And that's it. So that was part B. And we've got one final example. So this is example 25. So we've got insurance company needs to measure its risk if it's to underwrite a policy for major outdoor event planned. So the company used the following information about the region. Long-run data gathered about the region's weather suggests 75% chance that if today is dry, then the next day will be dry. Conversely, if today is wet, 72% chance the next day will be wet. And we've got the table given. So we want to find the probability it will rain in 3 days' time if initially the day is dry. So initially we start as dry. And which means our S naught is going to be, and we'll say 1 and 0. So we're starting at dry. So dry and wet. So wet's going to be on the bottom, dry is going to be on the top. Need to work out our transition matrix. And our transition matrix is basically these numbers in here. Just check our columns, our rows and columns are the same. So we've got dry on the top, wet on the bottom, so that's good. And dry and then wet, so that's all good. If they were the other way around, we'd have to change it. Which is why I chose dry and wet. So just fill in those numbers in there. And working out the probability it will rain in 3 days' time. So working out what S3 is. And S3 is going to be our transition cubed times our initial matrix. And if we do that, put your matrices in, cube it, or cube the transition matrix, and we'll get 5772, 75, and 0.422725. Okay, so it asks find the probability it will rain in 3 days' time. So the probability of a dry day 3 days after a dry day is 57.7%. So the probability it will rain would be 42%. Part B, find the long-term probability of rain if initially the day is wet. So we're saying initially our day is now going to be wet. So we've got dry and wet. And we want to work out the long-term effect, so the long-term probability. And to do that, we need to work out S of a high number. And if you remember from past video, 50 is a good number to choose. So if we go S of 50, we'll eventually get into what's called steady state. So if we do S to the 50, we'll have T to the power of 50 times our initial state, which was 0, 1. And if we do that on our calculator, it will probably take a minute to work out. So have a go at doing that, and you should get this answer. And so once you've done that, you need to just confirm that it is in its steady state, which means we need to do one more, so 51. And if we do that, we should get the same answer. Okay, and because they're both the same, we can say that that's our steady state matrix, which means in the long run, (47.2% chance it will be a wet day. If the initial day is wet. If we go back and just look at part C, so if the company insures only if they have the odds in their favor, will they insure the event? So we can say in the long run, there's a 52.8% chance it will be a dry day. So looking at this one here. So we've got 52% chance that it's going to be a dry day. So we can say there is slight in favour for the insurance company. So they will insure. Okay, so that's part C. So that's all we need. It's just summarising our results. And so that's part B, and we'll say A over here. Okay, so that's it. So that's chapter 8.8. It did take a while for this video to get through, and a lot of these questions are quite lengthy. The hardest part is getting that initial matrices out, and then using the correct um, recurrence relation. So have a go at some of the questions. Um, Thanks for watching. Sorry about the length of this video. It was quite long.